Lesson 2. Functions and mappings. A mapping transforms or turns a set of numbers into a different set of numbers. It can be described in words or via an algebraic expression. It can also be represented by a graph. Let's look at these three mappings. In this mapping, all of the numbers in set A are being mapped to a number in set B, with each one taking one unique or distinct output. A mapping is only a function if every input has a unique or distinct output. They're either one-to-one, like this. This is a one-to-one function. Or they can be many-to-one. They can have many-to-one or one-to-one. However, they cannot be one-to-many. You cannot have one input have several outputs. So this is not a function. A mapping can be turned into a function by considering its domain, which is all the possible inputs it can take. For example, take the graph y equals square root of x. If x can take any value in the real set, any real value of x, then it's not a function, as some values of x aren't defined. For example, x equals -1. You can't have the square root of -1, so it isn't mapped. But if you restrict the domain to x is bigger than or equal to 0, and you can write the function like this. You can write it like this, where f of x equals the square root of x, then you give the domain, where x can take any real value, but it also has to be bigger than or equal to 0. Let's look at 3 examples. For this first one, y equals 2x plus 5. Every input goes to one output. So the function is one-to-one, the mapping is one-to-one, and it is a function. If we take this, y equals 1 over x, it's one-to-one, but it's not defined for x equals 0, so it's not a function. It can only be a function if it's defined as f of x equals 1 over x for real values of x, such that x is not equal to 0. Every other value of x has an output except for x equals 0, so we have to restrict it to this. For this last one, it's a many-to-one function, as many values such as x and minus x can have the same y value, and it is a function. Let's do one final example. Let's take the piecewise function, which is defined as a function that can take different values based on the values of x. So it's composed of many functions in one. We'll see that for all x less than 1, it's defined as 5 minus 2x, and for x greater than or equal to 1, is defined as x squared plus 3. Let's sketch y equals f of x and the range, which means the possible values of y that f of x can take, and let's solve f of x equals 19. From x is 1 and less than 1, we can see it takes the shape of y equals 5 minus 2x, hitting the y-axis at 0, 5, and ending at 1, 3. Notice that because it's less than 1 and not less than or equal to 1, we use an open circle, and because it's greater than or equal to 1 at x squared plus 3, we use a closed circle to define this part of the graph. The range of the graph would be f of x, we want the range of f of x, is bigger than 3. It's not equal to 3 because it's not defined, because the y equals 5 minus 2x part is not defined at x equals 1. It starts at 4 again. So it goes all the way down to 3, but it doesn't reach 3. So the range is f of x is greater than 3. For the positive solution, for x squared plus 3 is 19, we get x squared equals 16, so x equals plus minus 4, but x equals 4 because it's positive. And for the negative side, we have 5 minus 2x equals 19, so 2x equals minus 14 and x is minus 7. So the solutions are x equals 4 and x equals minus 7.